Our final presentation today will be by Dr. Sarah Choyke. Dr. Choyke is the Technical Director at Eurofins Environment Testing in Arvada, Colorado. She has 15 years of experience analyzing emerging contaminants in the environment with expertise in analytical chemistry, sample preparation, and mass spectrometry. She received her PhD from Duke University and BS in chemistry from Haverford College. I know that many of us are extremely interested in her presentation topic today, so without any further ado, please start your presentation, Dr. Choyke.
Great. Thank you very much for having me. I'm very excited to talk about these novel reverse surrogates for the TOP assay. There were a number of collaborators involved in this project, and there is a paper that we are currently writing, so please be on the lookout for that in the near future. I really appreciate Rebecca and her introduction to PFAS, so I can sort of speed through that and get to the nitty-gritty of this presentation. As an overall, I will talk a little bit about PFAS and give you guys the background that you need, and then move on to the Total Oxidizable Precursor assay and EPA 1633A as our main analytical tools for analyzing PFAS and some of the PFAS that we can't analyze by normal targeted methods, and then give you a deep dive into these novel reverse surrogates that can be used for TOP assay. So as a brief introduction, which you've already heard, PFAS are a group of synthetic compounds mainly formed by the carbon chains with fluorine atoms. They're known for their water and grease resistant properties, making them really excellent chemistry products, but they are persistent in the environment, and the long chain PFAS have long half-lives in organisms, which result in some health outcomes. They are found in nonstick products, firefighting foams, and nonstick pans. So during my career as an analytical chemist, PFAS, the chemistry around PFAS has grown and evolved dramatically. As instrumentation has gotten better, we've been able to detect more PFAS. This started with a seminal paper in 2011 by Buck et al., who defined PFAS as highly fluorinated aliphatic compounds, and he suggested there were about 200. If we move to 2018, OECD came out with a new definition of PFAS that there were probably about 5,000. They revised this definition in early 2021 to say there were 6 million PFAS now, and EPA, the US EPA, came out with their own definition of PFAS and assigned about 15,000 individual compounds as PFAS. Whether or not they're all the same definition or not is up for debate, but I'm not going to question a definition. So at the same time as instrumentation is getting better and we're able to identify more, reporting limits are decreasing. So starting in 2009, we had UCMR4, and there were provisional health advisory limits for PFOA and PFOS in the hundreds of parts per trillion. In 2016, all of a sudden, those limits dropped down to 70 parts per trillion for PFOA and PFOS. And this is when I started getting interested in PFAS, because all of a sudden limits dropped by 10 times. And I figured something interesting was happening, so I jumped on the wagon. In the 20-teens, individual states started coming out with their own MCLs for PFAS in drinking water between 5 and 20 parts per trillion. And very recently, the US EPA came out with MCLs for PFOA and PFOS at 4 parts per trillion individually. And PFHXA, PFNA, and PFODA also were part of that list, although it is up for debate whether or not they will stay as enforceable MCLs in the future. Why am I telling you this? When we test for PFAS, we really have to consider what questions we want to answer. So the majority of PFAS testing is done by targeted methods. These are specific analytical methods for a set target list of analytes with known CAS numbers and analytical reference standards. They are, at this point, mostly EPA standard methods that have been multi-lab validated, although there are a number of user-defined methods that are still widely used in the industry. So these EPA methods are 537.1 for drinking water, 533 for drinking water, 8327, which is a direct injection for wastewater, but I wouldn't recommend putting gnarly matrix into your mass spectrometer. And EPA 1633A, which is for non-potable water, solids, tissues, etc. We also use non-targeted methods. So like I was saying, there are many definitions of PFAS that expand the number of analytes. And right now we have 1633A, which covers 40 analytes, but maybe there are additional PFAS, as Professor Weed just talked about. So non-targeted methods are an analysis where we're looking for analytes with unknown or known CAS numbers that don't have reference standards, or the analysis of proxy analytes. So this covers the total oxidizable precursor assay, AOF, EOF, or TF, so absorbable organic fluorine, extractable organic fluorine, or total fluorine, and non-targeted analysis. So when we're looking at targeted analysis, and I'll focus mainly on non-potable water and solids for the remainder of this presentation, we're mainly talking about 1633A. This is a targeted analysis of 40 PFAS. It was released not quite a year ago and is not promulgated, just as a reference. It covers matrices, a number of matrices, including non-potable water, soil, sediment, biosolids, leachate, and tissue. It uses solid phase extraction both for matrix removal and compound sample concentration. And most notably, it is a isotope dilution method. So it uses extracted internal standards, or EIS, for internal quantitation and non-extractable internal standards for normalization. So this uses a lot of isotopes. So when I say isotope dilution analysis, I want to give credit to my colleague Andrew Patterson for this analogy, but isotope dilution is a quantitative method that uses C13 or deuterated stable isotopes for internal standardization. So the analogy is, it's like you're off-roading on a dirt road in the backcountry of Colorado. That's your matrix and your target. And you put giant shocks on your car. These are the use of your internal standards. And it makes the cab ride very smooth. So this means that we can cover, so this is the most accurate and precise quantitation method that we have available to us right now. It is the gold standard for quantitation, but for PFAS. It means we can look at a broader range of matrices with a reduced potential of false positives and errors. This is fantastic. EPA defines the quantitative scheme that we have to use for 1633A in table 10. So this is a snapshot of that table. To the target analytes are on the left, and the quantitative reference standard is all the way on the right. And I do want to point out that as of last week, Cambridge Isotope released a new isotope for us to use for PFTRDA. So thank you for that. I have received probably 10 emails from various DoD, DOE, states, and etc., telling me that this is now available and I have to put it into the method as soon as possible. So I will get on that next week. So right, there's isotopes, there's 40 PFAS, but how many PFAS are there, and is 40 enough to get a good capture or a good identification at your site? So if we look at the PFAS chemical space, LCMS, targeted PFAS analysis, only covers a really small quadrant of the total PFAS chemical space. So if we take a step out, we can perform what's called the top assay, which converts PFAS precursors into targeted PFAS. This gives us a slightly broader scope, and this is what I'll be talking about for the remainder of the presentation. The top assay answers the question, how much transformable PFAS is in my sample? Or what is the total PFAS burden, potential burden at my sample? So traditional top assay takes PFAA precursors, uses hydroxyl radicals and heat, and transforms them into PFCAs, which are measurable by most analytical methods. So as an example, 6,2-FTS performed under the top assay will convert into PFHXA. So it preserves that chain length for the most part and converts non-measurable analytes into measurable analytes. There can be over-oxidation, under-oxidation, and I'll talk about that in a second. The top assay has gone under many facelifts. It is not always the most robust analysis because the oxidant can be consumed by the matrix. So if you have a heavy matrix sample, such as biosolids or wastewater or even AFFF, you can't produce enough hydroxyl radicals to complete the PFAS oxidation. Instead, you consume those hydroxyl radicals by the matrix and you get incomplete oxidation. So the solution that has been used is to add a reverse surrogate or some kind of tracer to measure the oxidation and transformation of terminal PFAS. And we have to consider oxidative transformation, interference, as well as the matrix. And these are just some examples of projects and funded resources that have been looking at updating, optimizing, and standardizing the top assay. And what I will be presenting is the next iteration of that. So this isn't a new concept. What people are using right now is okay. So reverse surrogates are used in the top assay. One of the main ones that is used is the C2 labeled 42FTS. This converts into PFBA, which is a target analyte. Not only that, but C2 42FTS is used in the 1633A quantitation scheme. So not only can we now not measure PFBA due to the formation of it, but we also can't use 42FTS in our quantitation scheme if we want to use 1633. Another reverse surrogate that folks are using right now is the 13C8 fossa. This is a long chain PFAS, so it's more characteristic of what you might see in a legacy AFFF transformation. Now, unfortunately, again, 13C8 fossa and the transformation product, 13C8 PFOA, are both 1633 EIS or quantitation internal standards. And so although this is a great way of using stable isotopes, it's not the best way for pairing top assay with 1633. Finally, many people also use the deuterated methyl fossa. This converts into PFOA, which is a target analyte in most cases, and the deuterated methyl fossa is also a 1633 EIS. So these are great options. They're not the best options if we want to use the analytical tools that we have. So a number of the collaborators that I've worked with had been working with Ben Priest and a group through EPA, specifically Troy Stock, Jean Van Buren, Ashton Collins, and Toby Sansa. Created new novel reverse surrogates for exactly these purposes. So there are 3 new reverse surrogates available, and I'll detail all of them quickly. So the 13C-PFNA is a C9 carboxylate, and it's used to measure extraction traceability. So it's stable through the oxidation, and it measures the overall efficiency of the method. 13C3 FPHPSA is a C3 sulfonamide, which I will refer to as sulfonamide for the remainder. And this is our reverse surrogate. It will be consumed through this reaction. Sulfonamides are precursors, but it creates the 13C3 PFHPA, which is a C7 carboxylate. None of these analytes are used in the 1633 quantitation scheme, and so they are free for us. They don't interfere with any of the quantitation, which means we can use them externally to 1633 to measure the oxidation. There were 4 labs that participated. UC Berkeley, Purdue, and Eurofins had 2 top approaches. What I want to convey here is we used a variety of top protocols, different volumes, different spikes, different locations, and we came out with very similar results with these reverse surrogates, so which was very great to see. So first, the 13C3 PFNA, this is our overall efficiency. We use parameters of 50 to 150% to say that this worked out really well. And across all experiments, pre-top, post-top, and top with matrix, we, two of the labs that I'll refer to here, recovered at least 50% of that overall efficiency. In different volumes, different procedures, etc. For the sulfonamide, we were looking for complete consumption of the sulfonamide or less than 10% recovery. In the pre-oxidation, both labs get very good recovery. We expect this. We're not oxidizing any of this material at this moment. And then during top assay, no matter if there were a clean matrix or an AFFF, both labs recovered less than 10%. So this is also a success. Now, this is where it gets interesting. When we wanted to measure the transformation product, so this is the 13C3 PFHPA, there's currently no precedent for this. Nobody is looking for transformation products of reverse surrogates. And this really shows us where we're doing well with top and where we could use some improvements. So with the pre-top, so no top, we get no formation, which is fantastic. With the top assay in blank matrix, both labs recover at least 50% of the carboxylate, which is awesome. Our top assays are working really well. But in matrix, we see consumption of the reverse surrogate, the sulfonamide reverse surrogate, but not exactly as much formation of the carboxylate as we were expecting. But this is great information for us because it means that maybe we are consuming a lot of the hydroxyl radicals in other ways. Maybe the sample needs a little more dilution. Whereas we didn't have quantitative information before, and now we do. I will speed through the next two slides. Again, why we measure this stuff, it's because we're not quite sure how many PFAS there are in the environment. And so we use top assay as a tool to get at those questions. So whether there's 100 and about 30 standards available, 200 to 300 PFAS in commerce, maybe 600 have been made either on purpose or inadvertently as side products. 17,000 is about the definition of the US EPA for how many PFAS there are, or maybe there are 7 million according to the OECD. So there's a lot of unknowns with PFAS. And again, top assay is a way to get at that information. So if I just want to give you a snapshot of that top assay in AFFF. So AFFF is aqueous film forming foam. It's between 1% and 3% PFAS with 15 to 20% hydrocarbon surfactants. So that should give you some blaring alarms for those of us who do top assay. It's about 20% solvent. There are additives and modifiers, water and diluent. And so there's a lot of stuff in AFFF that isn't necessarily PFAS. But for this sample, both labs got very good recovery of the PFNA reverse surrogate, which shows our just overall efficiency of the analysis. Both labs oxidized almost all of the sulfonamide precursor and formed between 30 and 40% of the carboxylate. So this is pretty good. We have learned a lot through this process, and we have a number of next steps to take. So with these collaborators, as well as help from folks at EPA, we are looking to revalidate, re-optimize the top assay protocols and provide guidance on how to set up these methods for complex matrices. And so please stay tuned for that. And please be aware of the new reverse surrogates available to use for top assay. So with that, I do want to thank all of the collaborators on this project and also Ben for the invitation to speak at Isotope Days. So thank you very much.
All right, thanks a lot, Sarah. Your presentation, I think, is very interesting and very helpful for a lot of people. And also thanks for the shout out on the perfluorotridecanoic acid. It's something we're proud to get out to everybody to be able to use. So yeah. I think, many of us realize top assay opens up a greater amount of information for PFAS precursors. And the work you presented will help with the robustness of the data being generated. So I think that's a really helpful thing. I'm pretty tied in with this, as you mentioned, so I don't really have, I'd rather open this up for any other people that might have discussions. You're the last presenter of the day, so we can take just a couple of minutes if anybody wants to add in some questions. Looks like we just got this. All right, question came in. When will these reverse top assay standards be available? They are available. They're in stock now at CIL, so we can reach out to you if you're looking for any of these standards currently. Does anybody else have any quick questions they'd like to add in? How much does it cost to process one sample? All right, you can answer that to some extent, Sarah.
I can. Top assay requires two analyses, so it's a pre and a post. The main goal here was to tie the pre-top with 1633A. So we have accomplished that here. We are working on getting that into production into our commercial laboratories. It is not available at this moment because we want a little bit more data, a little bit more optimization to get you those best numbers. If you would like a quote, please reach out and I would be happy to provide that for you.
Great. Okay. Anybody else while we've got our professional here on the line with us? Okay. All right. Well, I guess we'll move along. We're going to keep this open for a bit. So thanks very much, Sarah. We appreciate your presentation.
Yeah, thank you.
All right. So this brings us to the close of our Isotope Days webinar for environmental analysis. I'd like to once again give my thanks to all of our outstanding speakers for the time and energy in sharing these excellent presentations. You know, again, covering 3 different continents and presenters working with all of you to give you their information. So really grateful for their time and energy on that. As mentioned in the opening, our goals for today's webinar were to share information from leading scientists about recent analytical developments, to encourage further discussions in these application fields, to keep researchers informed about CIL's range of isotope labeled products, and promote engagement in worldwide research topics. I truly hope that you have enjoyed this webinar and have taken away valuable insights into these research topics.